So this is the PPT of my project titled Parallelization of Navier Stokes equations. I'm Ranjani.R pursuing MTech Embedded System Technologies from VTU. So this is my problem statement. Basically what I'm trying to do, what I have done is to parallelize the algorithm used for the iterations of the Navier Stokes equations. The Navier Stokes equations are actually used to model floods, and by parallelizing this algorithm we will be able to reduce the execution time of the algorithm, and hence we'll be able to predict floods in a much faster manner than what is being done now. So why this project I have selected is because it is the need of the hour, keeping in mind the annual flooding of the Brahmaputra and the flooding of the Uttarakhand region 2 years before. So we need means to predict floods so that lives can be saved. Of course, we cannot do anything about the property because it is immovable, but at least if people know that a flood is going to hit them at some point, they can move. So this includes the literature survey, the existing technologies in flood modeling and propagation. So the first one is website for monitoring floods using Google Earth and 3D GIS. Basically, Google Earth provides the photographic view of the Earth's surface, and using that the height values are extracted and a DSM is created, which is nothing but a digital surface model, and that and the Navier Stokes equations are then applied on this to propagate floods. Next one is the remotely sensed determination of flood surface gradients. Here what is happening is that basically the water, the color of water is near infrared wavelengths. So we locate this, and then the entire terrain of the nearby region is modeled using these frequencies and wavelengths, and hence the height of the water column is extracted, and using image processing techniques, basically the propagation of floods is done. The third one is a real-time flood monitoring system based on GIS and hydrological model. Basically, GIS is nothing but a geomatic information system, and what these people do is they take data like velocity of the water and height of the water from hydrological monitoring stations, and then again apply a variation of the Navier Stokes equations called the Saint Venant equations for flood modeling. The last but method, which is the method that I have also selected, is mathematical modeling techniques for flood propagation. There are two mathematical tools. One is CCHE2D and Anuga. For my project, I have taken Anuga because Anuga works in the Linux platform, uses Python, with which I'm very comfortable, and license-wise also it is freely, it can be used freely. So the existing system, in the existing system, the serial modeling of floods is done using Anuga, and it runs on a quad standalone computer, and they use only a single core. The limitations are that even simple flow models take a really long time to generate output. The obstacles actually are a large number of loops and large amount of data. The proposed work is to identify the various loops in the library functions and parallelize them using threads. Advantage will be that the time will be shortened. Resources used are high performance computing, obviously from the Center for Development of Advanced Computing. We have made use of the supercomputer Param Yuva 2. Next we have used the Anuga libraries. After that, the basic working model is that given a set of coordinates, a domain will be created. A domain is basically a mesh of triangles whose vertices are the coordinates, and the NS equations have to be iteratively evaluated inside every triangle. So this will give the level of water and direction of flow in each triangle at the end of the given length of time. So basically the first step is to compute the flux at the blue dots. Then the next step is to compute the time step, because since each triangle has different area, the time step will be different, so that information can never skip a triangle. The third step is to update all the quantities within the triangle. Fourth step is to update the quantities in the adjacent triangle, and the fifth step is to update the boundary values. So the initial hypothesis was to parallelize all the loops, but then this caused the extension of execution time, because the time taken to set up the parallel structures was greater than the entire execution time of the serial program itself. So this was abandoned halfway through, and we used a modified hypothesis in which we used threads to just parallelly execute the evolve method of the class domain. Here we have observed that from 41 minutes the time has reduced to just 6 minutes with 2 processes, and to 5 minutes with 4 processes, and 4 minutes with 8 processes. So thus we have seen that the time has reduced. So this is how the mesh is partitioned. The numbering is also different. The numbers in the bracket are the modified mesh numbers. Ghost triangles are used for the inter-triangle communication purposes, because every triangle needs values from the adjacent triangles to evaluate values within itself. Now the future scope is that the multiprocessing library, which was used in the current project, it crashes when we call it for the complicated programs. So there is a more robust library called pathos.multiprocessing, which can be used to prevent the crash. Also we can use PyPar library of Python to actually give each subdomain to a different core, and hence a multi-core approach can be implemented. These are the references.